Hi, in this lecture, we'll be looking at local probability models. So I'm sure you remember from the last lecture on Bayesian networks that was also on representation, where I defined exactly what a Bayesian network is, and it looks something like this. There was something like a structure where it had, we call that K, where there was also this idea that the Bayesian network was a surrogate for independence associations, which was denoted by I of k, something like this. And we said that these were faithful to, or we said it was almost faithful to some kind of I that is that governs a particular distribution P star. So there was this whole story about whether k is a good fit for this distribution, what can it capture, what can't it capture, and we ended up the lecture on Bayesian networks by saying, look, this is the total number of distributions, and Bayesian networks can capture quite a big part of these distributions, but there was a lot of stuff also that it could not capture. There were certain kinds of constraints or variable associations which could not be captured by Bayesian networks. And so we ended up saying that, look, we need a different kind of representation. So that was the representation that we would be talking about. The undirected representation would be the next lecture after this one, where we talk about something called Markov random fields. Okay, but so these Markov random fields, they come in different flavors, like conditional random fields and others. And we'll find out that having no restriction of the direction of the edges, or having undirected graphs to represent probability distributions, these kinds of PGMs actually offer lots of flexibility, and they allow us to do some really cool things, like maybe describe an image, because an image, you can imagine, doesn't need this kind of arrows. We can just model the pixels or the superpixels as nodes and the associations of the neighboring pixels using these influence relationships. So you can have something like this. This is called a Markov random field. And so this can describe, for example, an image. So there's lots of these ideas. And well, look, no matter what you choose, what kind of Bayesian network you choose, whether it's a Bayesian network or sorry, no matter what graphical model you choose, whether it's a Bayesian network or a Markov network, we need a way to define these nodes, these little circles. And so no matter whether it's in a Bayesian network, a variable like this, or in a Markov network, a variable like this, we still need to talk about what is this? How is it modeled? How do we model this particular thing? This particular node, this variable. Okay, so that's really what today's lecture is about. We're going to be speaking about those particular nodes, and how do we represent them. And it turns out that there's so many, because of those two assumptions we made in the very first lecture, when we spoke about those assumptions like the independence assumption and the alternate parameterization. If you remember that slide in the previous lecture, it allowed that idea of an alternate parameterization is really the idea of today's lecture. So we're going to be looking at what is called local probability models, and then after this we will look at temporal models, which is a different topic, but we've grouped them together like this so we can cover both of them at the same time. So we'll first look at these local probability models here, which is going to be tabular CPDs, deterministic CPDs, context-specific CPDs. We look at that, and then after that we will look at temporal models, because you would wonder now, how will the Bayesian network look in a case where we have a time element, right? So it unfolds over time like a trajectory. So we'll look at that after this. All right, so let's get started. So let's start with local probability models, and this is still under the domain of representation, right? Because we're still representing things. Well, the Bayesian network was a big representation on its own, but now representing the very nodes of a Bayesian network or Markov network or whatever, this requires some representation too. So that's what we're going to be talking about now. Okay, so let's begin. So what is this notion of independence in Bayesian networks? It allows us to factorize complex distributions. When we speak about complex distributions, we think about our joint distribution I mean, any kind of joint distribution is a complex distribution, right? I mean, you've got a lot of variables and lots of associations, and it decomposes into quite a number of possible cases. Different configurations of the variables into values give you lots of possible ways of perceiving the joint distribution. So that's something that one would need to think about. But if we use this notion of a Bayesian network, then we can represent this complex joint distribution into a product of factors, right? So then we got this idea of a product of factors, and that's where this, see where you can have the probability of D, the probability of I, the probability of the SAT score or the APS score, whatever, the probability of grade. So then this APS would be given intelligence, the probability of grade will be given difficulty and intelligence, the probability of the latter will be given the grade. And so we can multiply all of these factors together to give us the complex distribution, which is the joint probability distribution. So so that's really great. We know that already. But what we don't know, what we didn't discuss yet, is how, we alluded to it when we spoke about these tables, but how is difficulty actually represented? How do you measure, or how do you represent the difficulty of a course? How do you represent student intelligence? I mean, surely students can't just be categorized into clever and dumb, right? How can we represent grade? I mean, surely grade can't only take 3 values, as in the toy example from the previous slide. Surely a letter is more complex than either good or bad. I don't think that the professor on his desktop has 2 types of letters, either a good letter or a bad letter, and then depending on which student, he either chooses one from one of those templates and then just changes the name on top. I mean, surely it's more complicated than that. So the question really is, how do we represent these nodes? And if we look more specifically, how can we represent a grade? Like I said, you can represent it using symbols in a multinomial. You can represent grade as a continuous distribution, like this, where you have the 50% here, the 100% here, 0 here, and students' marks are all over this distribution. It's all over this normal distribution. So the student marks fall around this kind of curve. All right, so there is a lot of ways of representing grade. Just to look at grade alone. This is the frequency, by the way. This is the number of students who got that grade. So maybe 60 students got a 50 in the class. Maybe only 2 students got 100. All right. And then maybe a lot of students got 0. Maybe the curve goes something like this. Okay. All right, so the most obvious way of doing this is the way I've shown you how to do it, is using something called tabular CPDs from the previous lecture. And so when we are dealing with what we call discrete random variables, this can be a Bernoulli distribution. It's like every value, for example, x1 can either take the value x0 or x1, or it can be either true or false, or it can be black and white, or it can be easy or hard. So this Bernoulli kind of thing. Or otherwise, you can have discrete random variables which are multinomial, such as the colors of the rainbow, right? Violet and the other colors. Or it could be, it could be other kinds of multinomials. So you can think of you can think of those discrete random variables as taking on different kinds of multinomials, and it doesn't all of the random variables don't have to take the same number in the multinomial. For example, one can be a Bernoulli distribution, another one can be can take on 3 values, another one can take on 4 values, and I'm sure you remember from the previous slides when we spoke about Bayesian networks, we saw that grade had 3 possible values. However, intelligence had 2, difficulty had 2, the latter had 2. APS had 3 or something like that. So there was different numbers of values for each variable. Well, if we have discrete random variables, then we can use a table to represent them. Similarly to truth tables that you did in first year, where you would just write down the joint distribution with all possible configurations of the variables involved. So now the variables involved is not necessarily all the variables in the joint assignment, but rather just the variables for that particular family. So for example, if you have x1 and x2 and x3, the scope of this particular factor will simply be that of x2. right? The scope of this particular factor will only be x1, and the scope of this particular factor will be x1, x2, and x3 because they are all together. Because when we look at the scope of a particular node, any node, we look at itself as well as its parents. So we take all of those variables together and then put it together in the scope. So for example, the scope here is x2, the scope here is x1. However, the scope for this particular variable is x1, x2, and x3. All right, so that's what we mean. And so we can generalize this and say for any variable x, we take the parents of x as well, and that all of those variables give us the scope together. And the table that we use to represent these discrete variables need to contain every possible joint assignment of these variables only. And so we can look at an example of that just using 3 variables. So remember grade, for example, from the student Bayesian network. It had 2 parents. It had difficulty and intelligence. And those 2 parents were connected to grade like this. Okay, so that means that the scope of grade had to be itself, which was grade, as well as difficulty and intelligence. So the scope was those 3 variables. So what we need to do here is look at every possibility, assuming grade is just 2 values, difficulty is 2 values, intelligence is 2 values. We look at every possibility of grade with those 2 dependencies. So it's either they are all false, or obviously grade won't be false, it'll be a value. Difficulty will either be yes, it is difficult or not. Intelligence will be high intelligence or low intelligence. But just to simplify it so that we have a common vocabulary, we're just going to look at them all as either true or false. So grade can be true or false. Difficulty can be true or false. Intelligence can be true, just for the sake of having a simple to understand table. So they all could be either false, or 2 can be false and 1 can be true, or we could have this. I'm sure this reminds you of when you did, I don't know if everyone here has the same background, but in first year computer science, there is basic computer organization at WITS, and there it's like an introduction to computing course where you look at truth tables and circuits. And so in that particular course, you look at building circuits and building them using truth tables. So what you would then do is you also have this Bernoulli thing where every variable can either be true or false. And so you just list all possible configurations and then write down what the outcome would be. So for example, if you have A and B, then to write down all possible configurations, you would write them out like this, which is all the different ways you can write out A and B together, where each variable takes on either 2 values. All right, and then this is the kind of idea. So you would do that for all of the different variables, and then you would assign a probability to them. So this probability, where does it come from? I haven't told you yet. It can be learned from data. It can be elicited by an expert. But the point is that it comes from somewhere, and we can then put these values inside of this table, and it now tells the whole story about how that factor grade actually works. All right, so this is the basic idea. All right, so what is the problems with these tabular CPDs? So, well, they are very easy to understand. I mean, if you just show me a table, I know exactly how you got the table. Or maybe not got the table, but I would know exactly how the table operates and how the assignments are associated with different joint configurations, different joint assignments. All right, but there are several problems with using these tables, as you can imagine. All right, so variables with infinite domains don't really sit nicely in discrete values, and so we can't really store variables with continuous nature to a table. We cannot do it. The other problem is that the size of the table increases. It increases exponentially as the scope increases. So, for example, with grade we had 3 variables, so that means that we had 2 multiplied by 2 multiplied by 2 possible entries to the table. If we had another variable on top of that, it would be again multiplied by 2. If we had another one, and so on and so and so. I'm sure this sounds familiar. We looked at it on the first slide of the last lecture. You can see it's already 6 o'clock now, 7 o'clock. My eyes are starting to close. I'm sorry about that. So okay, so my point is that really the table size increases exponentially as the number of variables increase. So this here is illustrated by this idea where if you have 2 parents, you need 8 values, right? Why 8? Because it's 2, which is the the variable itself, and then the two parents, which are these two, and that together gives you 2 to the power of 3, which is 8. If you have 6 parents, then it's 6. So it's 2 times 2 times 2 times 2 times 2 times 2, and then the extra times 2, because you still need to do the, so it's actually 2 to the power of 7 for this one, and 2 to the power of 3 for this one, because you need to include the value itself. So the parents plus the actual value, the actual variable itself. So it becomes 7, 2 to the power of 7. So yeah, so I mean, and what about like if you have 128 probabilities in a table, where do these probabilities come from? I mean, we can't go and bother an expert for those probabilities. I mean, even if we do have some kind of way of surveying it, because there are so many possible values that we would end up in a situation where the patient will lose the expert will lose patience with us, and they'll tell us just to get out of here, I've got lives to save. So we need clever ways to learn when we have so many values, and often there aren't many clever ways when you have plenty of values, because every single probability in that table needs to be learned somehow. And so we should have at least seen some instances of that joint assignment inside of the training data, and if they're very rare, and we'll talk about the rareness of these things when we speak about inference, but if they are very rare, then we are basically hopeless in our attempt to learn those probabilities. All right, so a CPD, not CPT, a CPD, a conditional probability distribution, just needs to specify a conditional probability. How you do that can be in any way you like, right? It can do it in any way you like. So this is just one way of doing it, using tables. And what I'm going to show you is a few other ideas on how to do this. Well, the easiest way of doing this, the simplest way of doing this, without using a table, of course. I think the table is the simplest way, but the different way of doing it would simply be to use what we call a deterministic CPD. Well, in this deterministic CPD, we just have a branching statement that says it's either this or it's that. Okay, so you've got like, okay, your conditional probability association with a different variable, x2, and we just simply see if x1 sees this from x2, then do this, or else do that. Okay, so it's kind of easy. It's like an if statement in programming. So that's really the simplest non-tabular approach to this. And so here there's a mapping for the value of the parent, whatever the value of the parent is, and then if whatever we see there, we'll get a value of x. So for example, if the parent here gives us a particular thing, f of parent of x, then all we do is we output a 1, or else we output a 0. And so this is now just one parameter that we need to store if it does this. Otherwise, it always is going to do this. All right, so that's simple to understand. So for example, if x is continuous, then we can model a continuous function. So here there's the probability of x, so this is your x, and the dependency here is y and z. So we say if y and z give you a particular thing, then output that as x. So in this case here, the deterministic function is we simply add y, whatever the y is, to the z, and that becomes the value of x. And so that's basically what we do. We can also use other kinds of more complex functions, such as this one here. And this one is simply that you just take the value of y, you multiply it by 2, you take the value of z, multiply it by -3, and then you put it into this, add 1 after that, you add those three things together, and then you end up with the value of x. So then that becomes the output. Alternatively, you can use more complicated things, like you take the value of y, you put it in a sine function, you take the value of x, you put it in a natural exponent, and then you simply add them up and you end up with this x. So there's lots of ways of doing this. There's obviously dozens of what the big question is, does it do what you want it to do, right? So this is very modular in graphical models, but you do need some thinking behind how you set up these parameters. Okay, so the next way of doing a CPD on using a deterministic function, like I said before, is an if statement, and you'll see that this kind of makes sense in various contexts. So you might be saying, where on earth would I be using something like this? Well, here's an example. So if we all know how blood types work, and some of us did biology in school, and the blood type of a person really depends on two alleles, the G1 and the G2. And so we can model this we can model this based on those two alleles. And so the blood type of a variable X depends on G1 and G2. And so the deterministic function here is really with the what are these values of G1 and G2, and that determines what X is. So the first one is that we would end up with, it's deterministic in that there's no probability here. And also, as you notice in these, there was no probabilities associated with this particular idea. It was simply, if this, then do that. And this works really well here, because for certain we know that if the GA is if this allele is an A and this allele is a B, then for certain the individual will have the blood type AB. If this allele is a G and G2 is either an A or an O, then the blood type will be an A. If the first allele is a B, but the second is either a B or an O, then the blood type will be a B. Or finally, if the first allele is an O and the second is an O, then certainly it will be an O. So you can see we can hard code this for what probability 1 AB will occur if G is A and G1 is A and G2 is B. Okay, so that's really great. So you see that deterministic CPDs, they use, as I explained, it does not rely on probabilities. It's really an if this, then this. And so because it goes against what the usual definition is in a probabilistic model, where we speak about parameters and the probabilities of these parameters, we often annotate these deterministic CPDs with a different kind of notation, just because we want to separate the idea of using probabilities from not using probabilities. So what we do is we use this notation of a double circle over a variable where there is a deterministic thing. And so since C is deterministic in the left model, right? So you can see here it is deterministic, here it is not. If we know A and B, then we must also know C. So it's not probabilistic anymore, because we kind of like, if A and B are known, if this is known and this is known, then for sure we know this, because we just simply put it into the function and we suddenly know C. So we treat it also as observed. And so that kind of like, it reveals something interesting about this model, in that it kind of means that there's now this idea that this colliding variable from before is now treated differently. And so what we can say here is that before we weren't able to do this in Bayesian networks, but if A and B are known, that means we know this and we know this, that makes D and E independent. Okay, this wasn't true in the Bayesian networks with non-deterministic CPDs, but it is true in the case where we have deterministic CPDs, because knowing A and B automatically means we know C, which means that the influence now from D to E is blocked, and from E to D is blocked. So the influence has no way of going past, even if we just know A and B. So this is something to keep an eye on, because in this case it wasn't true, right? This does not hold in this network, because knowing A and B doesn't necessarily mean that we know C, right? This can still be a mystery, and so the influence from D to C can still flow, D to E can still flow, and from E to D can still flow, but in the deterministic case it does not mean that. All right, so that's interesting. And what else is interesting? Well, we should then, this is pretty interesting, so much so that we can rewrite the rules for deseparation that we did previously by introducing this notion that if we do know A and B and not C, then if C is deterministic, then we do know C, and so we can treat it as observed. All right, so it's kind of like a very simple extension from the old deseparation algorithm, but if you want to know more, you can read this page on the textbook, page 160. All right, so let's Let's look at a different kind of way of representing variables, not deterministic separation, but now back to probabilities. And so what we have here is an example of a context-specific CPD. So this is different from tabular CPDs. It's different from deterministic CPDs. It's a different way of looking at this problem. And so when we look at this table, this tabular CPD on this side, can you see tabular CPD? When you look at this particular one, we see here that there are some patterns, and I've highlighted the patterns in different colors. We see that sometimes we have this blue, oh, what is this color? This kind of purple color where they're all the same. And sometimes we have the 0.025 appearing all the time, and it's all the same over there. And then sometimes on this side we have these values that appear the same. So why should we store all of these redundancies if there's so much of repetition inside of our tabular CPD? So this is really the motivation for context-specific CPDs. And the idea behind context-specific CPDs is that we can break up the conditional independence assumptions into these specific cases so that we can write them down and we can recover the tabular CPD perfectly by just using this notion. But first we have to identify what is the context specificness of this particular table. So let's have a look. We need a way of writing it down. So let's look at this one. Here's an example. So we see that J in this, so remember before we used to write these statements for the actual Bayesian network, like for example, G is independent of SATs given intelligence, right? Oh, and letter, for example. Okay, so this is an example of how we would separate the we would block off the observed variables, and then grade would not be able to get to SATs. All right, but we can do this specifically. We could do the same kind of reasoning specifically for a table like this one. We're just looking at something different, but we observe the same kind of thing. So we see that J is context specifically independent, right? Which one is J? These ones, right? J is context specifically independent of S and L, right, given AO. Right? So a good way of reading this is the other way around. So look at the given part first. So it's AO. Right? So let's cancel everything that doesn't involve AO. So we just take everything off like this. All right. Then we're going to look at S and L, and we're going to say that J is independent of S and L. So looking at S and L, okay, you can ignore this one too, because now we got what we're interested in, which is this block. We see that as J changes, so J is O here, right? It takes the same value, 0.1. And then JO here takes the same value, but with a completely different set of S and L. And then JO again is 0.1 with a completely different set of S and L. JO again is 0.1 with a completely different set of S and L. And so what we're saying here is that no matter what J is, and even when J is 1, it takes on this particular value with a different set of S and L. J takes on the same value, J1, with a different set of S and L. J1 takes on the same value again. So it seems that JO will always be 0.1 no matter what S and L is, and J1 will always be 0.025 no matter what S and L is. And so we can write it down as J is contextually independent of S and L given A to be 0. So we're just saying, in other words, on this half of the table, that no matter what no matter what S and L change, if J is 0, it's going to be 0.1, and if J is 1, it's going to be 0.25. Okay, so that's really what we're saying here, no matter what the S and L is. And so now let's look at this a different scenario here. This part of the table. Let's look at this part of the table. And here we have when A is 1, which is this here, well, it's actually all of this, okay? But when S1 is when S is 1 as well, so that eliminates now this part of the table. So we're just looking at this part, this bottom part. Then J is contextually independent to L. right? Because J0 will always be 0.0125 no matter what L is. See, L is 1 here and L is 0 here, but J0 is still this. And J1 is always going to be 0.1125 no matter how L changes. All right, so that's basically the idea. And we can write out these contextual independence associations. Okay, so that's pretty cool. So we can write them out like this. So that's wonderful. And so what we ended up doing is we kind of summarized this entire table into these two. Well, we summarized this part of the table into this contextual CPD, and we summarized this part of the table into this contextual CPD. We haven't really summarized this part yet. This part we'll have to write it out as is because they are all unique values. All right, so that's pretty cool. Well, let's see how we can use this notion to build a tree CPD. So this is a different kind of CPD. So this one was a context-specific CPDs. Now we're going to look at a tree CPD, which builds on this idea. And so what this idea simply says is that, okay, now that you've identified the independencies, draw a tree with these independencies. And we can assert those probabilities. So here we're going to need a calculator so that I can show you how it works. All right. So let's have a look at this root node, right? Okay, so most of you have done computer science, I think, or applied mathematics, and I'm sure you've seen a tree before. So a tree is just simply a data structure. In computer science, they do a whole course on data structures, and you learn about graphs and trees and all of these things. But it's not really difficult to understand, even if you're not from the field. The tree is simply one where every node has exactly one parent, right? So for example, here one parent, 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 here one parent. Okay, so that's really what a tree is. In a graph, however, you can have more than one parent. So it's a data structure where that property holds, but in this particular case, what we did was we chose to segment the tabular CPD in a way that segments the different values of A's. So for example, because we can see there's lots of repetition on this side and there's some repetition on this side, we can segment the table like this by according to A. You don't only have to do it according to A, you can obviously segment the table in 4 different ways depending on the variable in your first step, because you've got 4 different variables here. But what we can do is we can segment it this way first, because then we get a really optimal cut of this repetition and this repetition. Okay, so if A is 0, right, then we can go on this side of the table where we end up with either a scenario where we're going to end up with an assignment that leads to a 0.1, like here, like here, like here, like here. All right, or we can end up with an assignment of 0.025, like here, like here, like here, and like here. So we can just segment that, and we can say, okay, so it's either we end up there or there, and so we need to calculate the probabilities associated with that particular outcome. So it's either we end up with a JO, in other words, or we end up with a J1, okay, because these change so much that they don't matter. It's in the segment of it is independent. The only thing that really matters here is the J, because that's the only place where we have consistency with the particular outcome. Okay, so let's then. Okay, so I just want to have this line here. It's important to have this line here, but I wanted to clean it up so you can see a bit better. But here we can say, okay, there's a probability associated with this, either a JO to get that 0.1 or a J1, which is going to give you a different probability. Well, how do we get these numbers? Well, to get these numbers, it's not that difficult. We have to add up all of these numbers together. So let's do it with a calculator. So if I have my calculator, and if I have 0.1 plus 0.1 plus 0.1 plus 0.1 is 0.4, all right, and then you're going to add 0. Okay, you can just multiply them. So it's 0.1 times 4 plus 0.025 times 4, and that gives you 0.5, right? It makes sense because these are all quarters, right? So you end up with 0.5. So what we can do now is we can say for the case where J is 0, we have 0.4 divided by 0.5, and that's where we get our 80% from. And then we can have 0.025 divided by 0.5. In other words, the sum of all of this is at the bottom, and then the individual, all the JOs are added together to give you this 0.4, and all the J1s are added together to give you this 0. So it's actually 0.025 times 4, which is 0.1. So sorry about that. This will be a 0.1, 0.5, and this is where this 25 comes from. This 2 comes from, this 20%. Okay, I hope that makes sense, right? So we basically, all we did there was we just simply normalized. This is called normalizing, right? So we simply normalized and we ended up with those probabilities. Okay, so that's the kind of idea. And so now we do it again. So once we segment this way, then we've actually eliminated all of this part of the table. Isn't that amazing that all of these parameters, 1, 2, 3, 4, 5, 6, 7, 8, these 8 parameters were just taken up by one independent parameter. Because from this 0.8, you can derive the 0.2 by just subtracting 1 from it. Yeah, so you say 1 minus 0.8, you get 0.2. So you don't need to store both. So from 8 parameters that we had before, we now only have 1 parameter, which is the 0.8. Or you could choose to store the 0.2, doesn't matter. As long as you have consistency and you're able to keep track of what you're going for here, because this will be the J0 and this will be the J1. Okay, great. I hope you're getting this. And in your mind, I want you to try to reverse engineer the process, right? How do you get from here to here? I'm showing you how to get from here to here, but how do you do it the other way? All right, so let's look at this case where A is 1. Now we're talking about this part of it. So now you can start again, the same idea. You can say, okay, here's some repetition here. So I can segment it according to, so this A1 I've already chosen, right? So we're here already. So now I end up with a smaller table. And it turns out that S1 here is where the repetition is. So you can choose S1 for the repetition. Okay, you can scratch that out. And we see here that, okay, where J is O, we have consistency, okay, of the same thing. And when J is 1, we have consistency of the same thing. However, we don't have that for L. So we can ignore L because it's JO seems to be contextually independent of LO, or J in general is contextually independent of L. So we don't even need to separate it in context for that particular statement. So in other words, J is contextually independent of L. All right, so because given A and S. All right, given A1 and S1. I remember from before, A1 and S1. Okay, so we have that, so we can then just simply add up all of these values together. You get a number, and then you simply add these two up and divide by that sum, and then you end up with this and this, respectively. See how easy it is. It's not difficult at all. All right, and so we do the same thing with L. We can segment it further. But in this case here, we can't get away from the fact that since there is no repetition here, let me just highlight it. Since there is no repetition in this block, we have to write out all of the probabilities in normalized form for when we break it up according to L, where L is 0, and L is 0 and L is 1, okay? And then we got to break up those probabilities for the different values of J, J0, J1. Okay, simple enough. So we see that what cost us 16, if I count these up, 1, 2, 3, 4, 5, 6, all the way, you end up with 16 parameters in this table. Now can be replaced with only 4 parameters, 4 independent parameters. We can just store the 0.8, the 0.1, the 0.4, and the 0.9, and the 3, and we're done. Okay, so that's really cool, very useful. So let's now talk about this another way of representing contextual specific CPDs, and this is using rules. So we find that the tree, in terms of a tree, we have this contextual understanding of the CPDs. Well, this came from this general idea of having these rules, right? So we had these associations or contextual specific probability. So context-specific conditional probability distributions, right? That's what it is, and we came up with this tree. But you can write the rules on their own, right, from the tree. So for example, if you go to A0 and J0, you get 0.8. If you go to A0 and J1, you end up with 0.2. If you go A1, S1, J0, you end up with a probability. If you go A1, S0, L1, which one is that? A1, S0, L1, J0, 0.4, or 0.6. Okay, so we can read off this table and come up with these different rows. This is a row, right? This, I don't know how you pronounce it. It's this is how you draw it. It's like RO, row. I think it's RHO, not sure. But we say it row. It's a symbol, a Greek symbol. Okay, my point is really that this is the notation we use for the rule CPDs, and so we can just write down the rules as they are from this tree derivation, and then we're done. So it turns out that the way doing it with a tree and listing the rules, they have certain limitations. Both of them have some problems, right? So the tree is very easy to visualize. It's really nice, and you know, you can look at it and you can make sense of it, right? But the problem is that the tree is very limited, because it turns out that you can write certain rules like this that can never become a tree. So in other words, you can always go from here to here, but you cannot always go from here to here. And so rules can be sometimes more descriptive, more specific. They can be more powerful to describe these complex CPDs, whereas trees, on the other hand, are more visual. So obviously, depending on the application you would be using it for, you would be using other kinds of things. You would have a preference for one over the other. All right, so I also want to say that there are other context-specific CPDs like multinets and similarity networks, and although I don't talk about them in this course, I do want you to know that there are dozens of ways of representing variables. We haven't even spoken about continuous distributions yet, and just discrete alone, we had so much to talk about. All right, so the next part of this lecture, I'd like to talk about template-based models. And this one here is a very interesting lecture, because everything I taught you was for what we call static environments, where there is no temporal dimension. So in other words, cross-sectional data. But it turns out when you have a trajectory, you can actually build a Bayesian network. You can build a Bayesian network that is persistent through time. All right, and this is quite cool, because if you do this, then you can describe trajectories. You can describe the trajectory of a rocket or an aeroplane. You can describe students' success through first year, second year, and third year. You can describe the financial stock market, and you can use these models for all sorts of things. And so let's talk a bit about it now. And you might find it in your honors research. I don't know what everyone is doing for their honors research, but you might find it to be extremely useful if you do have trajectories to follow or to learn. All right, so let's start with the problem statement, right? So we know that PGM, so far the ones that I've taught you about, they specify a joint distribution over a set of random variables. So these random variables, this x can be x1, x2, x3, up to xn, and these can tell you things about anything, basically. The velocity of a taxi. It can tell you about the variables involved in giving you cancer, or the variables involved, or the objects that contribute to an accident, right? So there's lots of interesting scenarios where you would have these kinds of variables. In machine learning, we explored quite a lot of really cool scenarios. I'm sure in your other machine learning courses, like computer vision and NLP, you must have seen examples of what these variables can be. So in many complex spaces, we have two different cases, right? So the one is when we have a temporal setting where we have these variables, but they are changing over time. So for example, the weather, the wind speed constantly changes, and it changes in a continuous way. So 1 minute the wind speed is, I don't know, 3 knots per hour, or 30 knots per hour, and then it changes, becomes higher, and it goes lower. By 12 o'clock, it's like a hurricane outside, and then in the evening, it settles down a bit. I don't know if you noticed, but lately, around the evening after 7, there appears to be no wind at all until after 9, 10 o'clock when the wind starts coming back. Maybe it's just where I stay. But my point is really that there's these fluctuations over time. So you can think of your time as being a graph, whereas the x-axis is the actual time. It can be in hours, in seconds. Usually there's a granularity that has to do with our sensor, which collects the information, and that's basically where we get the readings from. And then here we have something about it. So it could be the frequency or the knots per hour or whatever, the barometer, which gives you the pressure in a particular area, but it fluctuates, and you'll see with time, this is just one variable, x1, but then for another variable, maybe this is x2, this one also fluctuates, okay? Maybe the speed of a taxi across the day also fluctuates, and this is going to be x4, and so on. So these different x variables, they're changing over time, weaving around, and we need to now capture these complex associations. Well, before we would capture things on a case-by-case basis, what we call cross-sectional data, where we are just given a timestamp of reality, maybe all of this marks for the PGM exam and some characteristics of the student. So that's one snapshot at the end of the course about everything. But here, what we have is maybe a student trajectory. Their marks are changing module by module. It's going up and down, and there's lots of other variables at play which impact those marks. Okay, great. So we want to understand, we want to make predictions over this kind of space. We want to be able to, we want to do a lot of cool stuff with this. We want to predict maybe a particular variable or how a subset of these variables will behave. In financial data, for example, we want to predict trends or the return on stock or whatever the case might be. All right, and you'll find a lot of what I teach you is applicable to financial analysis, and these are the methods of choice because they are completely explainable. All right, so another really interesting case that PGMs has found a lot of success in, because they're completely transparent, is in medical data when we have to monitor patients in an ICU. And some hospitals are using PGMs to do this because they are, like I told you, explainable, and we can calculate with evidence, as I've shown you in the previous lecture. So we hook up a patient to a bunch of sensors, and we learn how the sensors talk to each other or how they influence each other through observing things about the individual who is the patient who is in the ICU. And we can predict things like when their blood pressure will go up, at what part of the day will their blood pressure go up, if they are given particular medication, what is their risk of death or stroke, perhaps, if certain conditions are met at a particular time of the day. It's very interesting to actually see how these things are used. Okay, other ways of using this kind of analysis is on robot localization, right? To be able to find out how a robot or an agent should behave when it encounters specific environmental factors. So this is another example. In a lot of reinforcement learning, we have this notion of trajectories where we're learning from interacting through the environment, optimizing a policy. Okay, great. So very interesting. So another case of where we would require these template models is in a case where there's lots of repetition inside of the problem or inside of the context. So for example, in genetics, a family tree has this parent-child relationship over and over again. And the way the interaction between the genes occur happens over and over again. And so having PGMs kind of like a template model, a template-based model, can also be very handy here because we wouldn't have to write out the same model 10,000 times, but rather just write it out in a modular way so that it can unfold on its own as it is needed. Right, so it'll be really great if we could create this template class of for PGMs so that we can unroll them as needed for either temporal based problems or problems where there's lots of repetition, and we can have these these graphical models unfold as much as we need them to. All right, so the a Bayesian network is one way of modeling static scenarios, but what we would call a dynamic Bayesian network. This word dynamic, this relates to the temporal changes over time, and so these Bayesian networks now unfold over time. They unroll, in other words, over the trajectory to describe different parts of the trajectory. And it's really useful, as you can imagine, because if we have a Bayesian network that can do that, it's able to track system dynamics over multiple trajectories. And we can use the various trajectories of data to train a dynamic Bayesian network. And so we can then be able to do all of the cool things we can do with Bayesian networks, like the whole reasoning under uncertainty, incorporating evidence, and so on, in a temporal setting. So we're inheriting all of the powers of normal Bayesian networks in a temporal setting with these dynamic Bayesian networks. Okay, great. So let us define some notation before we actually start with understanding how these dynamic Bayesian networks actually work. All right, so let's start with this. So the first thing we need is a set of variables, right? Then we need these x, and this x, obviously, like I told you before, x1, x2, x3, x4 are different kinds of variables, but now we have this notion over time, so it unfolds over time, and because it unfolds over time, it makes sense for us to associate a little t value with each of these x's, these capital X's, so that we can track them. So, for example, x1 over time, t can be broken up into the sequence x1 t1, x1 t2, x1 t3, x1 t4, and so on, as long as we need, right? As much as time allows. And if we plot this thing, we might get something like this, where x1 is moving across time, where x is the time, and the y value is the value of x at that specific time. Okay, cool. So that's set. So that makes sense. And we can refer to xi, this x of 1 or x of 2 with this t, as a template variable. So mustn't forget the t. That's the template variable. It changes over time. And of course, we can define a set of all different x's, so x1, x2, x3, as the set of capital X, where it's a whole entire set of capital X bolded like a vector. There is a whole, this here is an entire set of these x1s and x2s, x1, x2t, a whole bunch of these temporal variables, and so on. And you can use this notation here to define the values of these temporal variables at different branches of time. All right, so it seems simple enough. I mean, there's nothing too difficult about that. But in order for this to work, we need three assumptions. Okay, the first assumption is, well, what exactly is the values, or where do these values of these different t's come from? Well, very naturally, in machine learning, when we often want to do some kind of analysis, we use sensors, like I told you, a barometer to check the air pressure, or other kinds of sensors to check maybe the wind speed or the temperature, the thermometer, the thermostat, or whatever. All of these different devices can be used, and because these devices are electronic, they are discrete, which makes them well, I mean, not that it's always going to be discrete, but most of the time they are. And because they are this way, we can actually use the granularity, that is how often those sensors actually take those readings, as our times, as our t's. So we normally use that these time slices to actually be the granularity of our sensors. Well, that's really great. So now we've got a way of reading data, right? So we can achieve different based on the sampling rate of our particular sensor, we have different values of our x's at different periods of time. So from this assumption, we now can break up our the joint distribution over all of the variables, which is x1 all the way to xn, for the entire period of time from the first granularity, which is the 0, up to the last time slice, which is the t. And what we can then do is we can say, okay, great. So the first variable will just be the first time slice, and then from this moment onwards, it'll depend on all of the previous ones. So this kind of looks scary, right? So in other words, what this is saying is that for our first XO, for all of the variables X, so this is the whole set of variables X at the first time slice, right? That doesn't depend on anything, but all of the variables X for the second time slice, which is actually going to be number 1 in this case, depends on everything from the previous one. That means it depends. So X2 here depends on X1. And then we can then do the same thing and say that X3 here depends on everything from before. So this includes this one and this one. X4 here on the fourth time slice depends on everything from before, which includes X1, X2. Doesn't this look familiar? X5 here depends on X1, X2, X3, X4. Doesn't this look crazy? But this is exactly what this equation says. And this looks familiar also. It reminds us of the chain rule for probabilities that we saw before. Well, this is the correct way of doing it, but for the same reasons that we didn't do this before, which is mostly because it's too complex to do it this way, and we'll end up with factors which are extremely large, we'll introduce yet another assumption to be able to make it a bit simpler. So instead of depending on everything from before, we are now going to say we're going to use the Markov assumption, which only depends on the previous time slice, and that's it, not all of the other time slices that occurred before. So here now we finally have an idea like a Markov chain, which tells us, okay, this time slice depends on the previous one and only the previous one. The next one depends on the previous one before that. The next one depends on the previous one before that, and so on and so on. We don't have this weird, crazy dependency structure anymore, but rather a very clean chain-like dependency structure between the time slices. All right, so that's the Markov assumption. So the question really is this a reasonable assumption? Is this a reasonable assumption? And well, you can think about it and you'll probably say no. Well, of course not, right? I mean, my behavior today isn't only dependent on my behavior from yesterday. It also depends on what I did last week or the week before that or 30 years ago. Well, I'm 32 now, but you know, some time ago, there was some learning lessons at different parts of my life that influenced the way I behave right now. So, of course, not everything is based on this forgetfulness assumption. So it might not be a reasonable assumption. But then what would be reasonable is for us to enrich the space, choosing x's that sometimes capture seasonality inside of it. So choosing an x1 which might aggregate other feature information as we move through so that we can capture our lessons learned and enrich the search space. So for example, when predicting financial data, we don't only look at yesterday's information, but we have a variable inside which talks up to seasonality, and maybe that variable can inform us about how particular stocks would move around, given that it captures seasonality from previous years, for example. So enriching the search space is enough, and that will make this a reasonable assumption. But on its own, this forgetfulness is very dangerous. Okay, so the last assumption that we'd like to talk about here is this notion of stationarity. And stationarity is a very easy to understand assumption. It's also called time invariance. It's also called homogeneous assumption. And really what it means is that the system dynamics doesn't change. So as part of specifying a temporal model, you need to decide exactly what is the structure of the model, as in the variable associations for every time slice. So let's say that the x1 to xn's structure is going to be this kind of conical structure. And of course, there will be dependencies across time from these. They'll all talk to each other from the Markov assumption from one time slice to the other, where this is one time slice, this is another time slice, this is T0, T1, T2, and so on. But what the stationarity assumption says, it says that the dynamics, the way these variables interact, remain the same, which means that the structure doesn't change. This structure will be the same as this structure, which will be the same as this structure. And if we do this, we keep the model, the system dynamics constant, even though the variables are evolving. Is this a reasonable assumption? Well, you might say, no, of course not. The system dynamics change because variable associations sometimes become relevant and other times do not. And while this is true, again, you can enrich the arrows or capture spurious edges so that they could later be useful, so as to not complicate the stability of the invariance when progressing from time slice to time slice. Because all of that, remember, the more complex your model is, the more you would have to switch around. So I would suggest that number one, if you do have system dynamics that change, I would still suggest keeping the time invariance assumptions, because if you have, like I said, enough tolerance or enough spurious edges which can capture more complex distributions as it evolves over time, then that will be enough to be able to change the model on the fly, rather than having to reconstruct the model at some arbitrary time slice. And that affects the learning, it affects the other assumptions that we made, and the way they connect from one time slice to the other. All right. Okay, so that's really great. So we've come up with this really cool model with these three different assumptions, the granularity, this notion of time slices, and then we spoke about the Markov assumption, and then we spoke about the time invariance assumption. And these three assumptions together tell us really nicely how to build a two-time slice dynamic Bayesian network. So what we would then do is we would say, okay, great, we just need some initial state distribution, and then we need some transition model. So that's the two-time slice Bayesian network. Here's the first one, here's the second one. The first one is just a static, a normal Bayesian network, which is how the system dynamics will work and how the parameters will be set up. And then the transition model is then, okay, we're now going to be able to have something that unrolls over time that also has exactly the same structure as the initial state distribution. And so we can do that simply by keeping a model for this and a rolling model for this. All right. And how do we define it? We define it like this. We say that the next state depends on the previous state, and the previous state, in this case, the next state depends on the initial state, which is this number one, which is equals to just simply the way each variable decomposes with respect to its parents. And sometimes the parent can even be in a different time slice. All right, so here's an example. So here's an example. This is the initial state, your I, and then this is the rolled network. So the rolled network just looks like this part here, and it simply unrolls over time. So here's time slice 0, time slice 1, time slice 2, time slice 3, and so on. Let's look at this a bit more carefully. Well, more just to learn the different kinds of notation associated with dynamic Bayesian networks. This is an example of a dynamic Bayesian network, DBN. Yeah, so let's first look at this. This is a template factor. So the probability of S1 given S0 is an example of a factor. It's this factor. And then this factor is the probability of O1 given S1. There are other factors as well, right? You can write down this factor, this factor, this factor, and this factor. But I'm just giving you an example. Okay, so that's really great. Then we have different kinds of time slices. We have the inter-time slice edge. These are the ones that are the dotted lines, the inter-time slice edge. They go between the time slices. Okay, so they are these ones over here. And these ones connects the variables between time slices. And so, here your influence of the variables is greater than your granularity. So, for example, a whole bunch of sensor data fits into one time slice. Another whole bunch of sensor data fits into a different. So you can pick the sampling rate. Not the sampling rate, you can pick it according to your sensor, but then you can group a whole bunch of those samples once it comes from your sampling rate to learn this aspect of the trajectory. Okay, so it's very interesting. All right, so then let's look at the next one. Then you get the intra time slice edges. These connects the variables within the same time slice. So for example, here where I circled it in green, this is an example. The solid line is a example of an intra time slice edge because this fits within the time slice on the side. So if you're still confused about what a time slice is, let me draw it for you. This is an example of a time slice. This is 0. Here's an example of the time slice 1. Here's an example of the time slice 2. Here's an example of a time slice 3. All right. And so the intra ones are all of the ones that connect the variables. You could have had many more here, but here we're just showing one. Then you get persistent edges, and these are the variables. Sorry, now these were about edges. Now these ones are about variables. Oh, sorry. This one is still about an edge, but this one is about a variable. Okay, so your intra-time, okay, great. So the variables persist with high probability. So this is an example of one that persists through time, always persists. It's going to always be there. And then you get the persistent variables, which are also template. So you see that this observable variable here is a template, but it does not, what you learn here stays here in this time slice alone. Whereas the persistent edges and the persistent variables, they are learned between the time slices, which means they share data from different time slices in order to be learned. And that's pretty important. That's what makes the persistence part of it, being able to go across the different time slices. All right, so that's easy to understand. And now we can finally define the dynamic Bayesian network. So a dynamic Bayesian network, very simply put, is a pair. It's the initial one, which is the one I showed you here, this one here. And then it's the one that rolls over time, which is this one over here. And this one unfolds over time. All right, so that's the notation, and then you can simply unroll the network as much as you want, up to whatever timestamp you want, whatever makes sense. And these are all design choices, depending on how big the trajectory is, how much data, or what you're trying to learn, you would unroll it in that way. So there are several examples of where we use this. So here's an example of a factorial HMM, an HMM, which is what we call a hidden Markov model. And this hidden Markov model is used in practice to distinguish several sounds playing on a single microphone. So this is an example of a bird, maybe. This is an example of a guitar. This is an example of a person speaking. Here's another person speaking. And this is the microphone. And so what happens is that this HMM actually learns how to separate these different voices using some probability distribution. Another example of a dynamic Bayesian network is this idea of a coupled HMM. And the coupled HMM is also extremely powerful. And what it's used is it can monitor the temperature of a building, for example, by having sensors in different rooms. So for example, here's a room where you have some so these, where it's shaded, these are observations, right? I should have mentioned that before. So here's an observation here. These are observations here. And they tell you about something abstract, which are the voices. Okay, so in this case, here's an observation here, and it tells you something about the something that's hidden, in this case, the temperature. So we observe something in a room, and it tells us about this temperature, and then we observe another temperature in the room, and it tells us something about the different temperature. But we also notice that there are neighboring variables which share information. Whenever influence can flow this way, and so the variables then share information about the temperature in adjacent rooms to tell you something about the overall temperature of the building, and perhaps even where possible health and safety vulnerabilities are. All right, so interesting, right? I know it's a bit dry to follow all of this, but maybe you can think about the applications of where you could use this, and then it'll become a bit more exciting. So maybe you got a very cool video game that you want to write an AI to play, and so you can use this notion of a hidden Markov model to share sensor information, maybe between agents. And you can think about how you would actually go about implementing something like that. That's extremely interesting. It's just something I came up with right now, but you can actually use it for that. It's a proper use case. Right, so Right, so that's really great. I spoke about dynamic Bayesian models. I want to now talk about something different. It's also a dynamic model, but it's called a state observation model. So really, there are dynamic models and then there are state observation models. So a state observation model is a dynamic model, except that the state observation transitions can sometimes move across the same states over and over again. So here we wouldn't have that. Here we would unroll it over time and monitor something across a period of time. Here the same thing, here the same thing. But in this particular graphical model, this is a different kind of PGM. Here we can move between states. So we can switch between states depending on what we observe. So for example, maybe you see today I'm walking around with a hat on and I've got gloves on, and then you can infer that I'm feeling cold based on that. But then tomorrow, you see me with shorts on, and I'm wearing sandals, and I am lots of shorts, and maybe then or a different kind of hat, and then you'd infer that I'm feeling hot, right? So then the next day you see me again with the gloves and stuff, and you say I'm cold. So you can see I'm switching between states based on observations. This is what a state observation model actually does. So this is another way of representing a process, and we generally use these models across different kinds of problems where we have noisy sensors, and these models are the method of choice for explainable learning inside of speech recognition problems. And so you can see it's predominantly deep neural networks for speech recognition, but when we do have explainability constraints, we always use hidden Markov models, which is a type of state observation model. All right, let me try to wrap things up quickly. I'm falling asleep here. All right, so for these state observation models, we need several things. Number one, we need a transition model, which allows us to move between these different states. And then we need an observation model, which allows us to do something based on what we observe. So the two different PGMs that we use for this is hidden Markov models and linear dynamical systems. So hidden Markov models is the method of choice, like I said, in its explainability for speech recognition problems, for robot localization, where we want explainable methods to do these kinds of things. And then also other state observation models, which are the methods of choice now for GPS tracking, is linear dynamical systems, also called Kalman filters. They're called Kalman filters, and this is what we use for even to track where the aeroplane is from the station. Okay, right, and these are all done with noisy measurements. So here's an example of the first one, a hidden Markov model. So we can see that we have several states. Here's a state, here's a state. These can represent different moods. They can represent different states of mind. They can represent like happiness, anger, something that's latent, something that is abstract. It can represent something like that. And then here we have the observations. These are the things that you observe about the person before making that judgment of what they are, or whether they're angry or whatever. And so you can move around this particular distribution in that way to be able to track their mood. And what's also really interesting about this is that it predicts what is the most likely thing to happen next. So when someone is angry, maybe the most likely thing there is happiness, or maybe the most likely thing after the anger is sadness. And so this kind of model can keep track of something like that. Obviously, there's more to it than just, there's lots of applications of this if you read about them. All right, so the hidden Markov model is made up of two things, like I said before. We've got this transition model here. That's these lines on the top. All of this is the transition model. And then we have the observation model, which is this thing at the bottom. And this is now tells us how to switch between these different states, how to make these particular occurrences. Right, so let's have a look at how this works. So here we got a transition state at the bottom, and we can see it looks like a matrix. So remember what a matrix is. And we see here that to move from S1 to S1, we can move from S1 to S1 with probability 0.3. So that's easy. There we go. We can move from S1 to S2 with probability 0.7. There it is. You can move from S2 to S3 with probability 0.4. There it is, and so on, and you can derive all of these different transitions from this matrix. Obviously, if you add more and more values into this matrix, maybe you won't be able to visualize it as nicely. So let's actually turn this into let's assume that we're given this hidden Markov model, and here it is, and we want to be able to calculate something about it, right? So let's start off with a new hidden Markov model, and this is a question for an exam. Maybe I can ask you this in the test. I most likely will ask you this in the test. So if I could just have a sip of water, sorry. Right, thank you. So we can we can answer the question like this. So what is the probability of observing the sequence 0, 1, 2 given the below hidden Markov model? And the hidden Markov model is denoted by lambda. So this whole thing here is lambda. So let's see. How do we do this? Well, let's start here. The first one, I mean, look how it looks very complicated, right? So we're going to go through it slowly. Right, number one, we look at the hidden states, right? There are 3 hidden states. How many observable symbols are there? There are 4. Okay, so so I'm guessing it's going to be 0, 1, 2, 3. These are the observable symbols. Okay, and then there's a transition probability matrix, right? This is what it looks like. And then there's the observation model. Remember that it has the probabilities of all these different observations, given the 3 different transitions that we can have. So the transition matrix here is, we've seen this before. If I go to the previous slide, we see it here. Okay, so it looks like this: S1, S2, S3, S4. You can write it down if you want. S3, S1, S2, S3. And then the observation model, we have 4 different observations. You can either observe a 0, a 1, a 2, or a 3, and this can be either for S1, S2, or S3. All right, so we map it out like this so we can understand exactly what's going on. So the first thing we want to do is draw this transition model. We want to draw this part of it. Right, so let's draw it. So this is what it looks like. Okay, if we draw those transitions, as I've shown you on the previous slide, we end up with a model that looks like this. All right, so we see that there are 3 different observations, variables, but the observable symbols can either be 0, 1, 2, or 3. 0, 1, 2, or 3. 0, 1, 2, or 3. These are the different values that each observation can take. And so what we want to do now is we want to calculate the probability of observing this sequence. Right, this sequence, for me to see a 0, 1, and 2. So you can do this with heads or tails as well. For me to see a heads, a tails, a heads, and a heads, right, and so on. Here we're looking at observing the symbols sequence. 0, first is 0, then a 1 after the 0, then a 2 after the 0 and the 1. All right. We want to calculate how. We want to basically calculate that. So there's an algorithm to do it, and it involves different steps, and I'm going to ask you to do this in one of the tests. So you got to know how to do this. Right, let's start off with step 1. So for step 1, we need to calculate initial state probabilities with the first symbol. So we start off with t is equal to 1, and we are starting off with the first symbol here, 0. So we need to calculate the probability of starting in each of the possible hidden states. 0 for this particular symbol. So we need to compute what we call the forward variable, which is denoted like this. And the forward variable is simply the probability of being in a hidden state I at a time t given the observed sequence up to t. So it sounds like a mouthful, but there's a systematic way of calculating this. So recall that the initial state probabilities was given to us. Here they are. Okay, these are the initial state probabilities. These are the ones that for each state, I have a probability of 0.6 to start in state 1, 0.2 to start in state 2, 0.2 to start in state 3. Okay, so I write them down here. I check. Okay, so we recall that. So now, like I said before, because we are dealing with 0 here, we have to look at this part of the observable model where there is a 0. So we're looking at the probability of being in each of these states for this particular observable symbol. So state 1, state 2, state 3. So now it makes sense, right? So we just compute it by substituting 0.6, 0.2, 0.2, 0.3, 0.2, 0.3. And so we end up with these forward variables for the first time slice. Alpha 1, alpha here t, where t now is equal to 1. See, I wrote it here at the top. T is equal to 1 for the others as well. Okay, we're going to do the same thing again, but now we're going to remember what those forward variables are. We updated them. So now these are now my forward variables. So now we're going to look at this symbol, which is the 1. And we're going to remember that, like I told you before, we need to calculate this for every, we need to calculate, oh, here it is. Okay, the probability of being in a hidden state I, right? Hidden state I, which could be S1, which could be S2, which could be S3, at a time t, in this case t was 1, now we're going to move to t is equal to 2. For the observed sequence up to t, the next sequence is going to be 1. So we move to this one. So in other words, we're going to do this slide 3 times. We're going to calculate these transition probabilities for these forward variables for the first set of S. Then we're going to do it for the second one. Then we're going to do it for the third one. All focusing on this observable symbol. So it's going to be first for the first S1 here. Then the next slide we'll look at S2, which will be 0.2. And then we'll look at the S3, which is going to be 0.3. I'm just, foreboding what's going to happen next. But for now, let's keep things simple. So we're first going to do the calculation for the first forward variable, which is going to be x of 2 for the second time slice for the symbol 1. I hope you're following. If you're not, then I've color-coded it for you. So the way we calculate this first forward variable, we're going to do it for the second and the third as well, but we calculate it like this. We say, okay, the x1, the previous forward variable was exactly 0.12, multiplied by the A11, which is going to be 0.7, multiplied by B11, which is 0.3. B11 doesn't change, see? It's the same. On the next slide it'll be B12. On the next slide it'll be B13 to calculate the forward variable. Okay, so you plug in all of these variables and you end up with 0.0342. We do the same thing again, but except before we looked at this state, right? Which was the first state, S1. Now we're going to be looking at the same thing for the second state. And because it's the second state, we're also going to be looking at the probability of seeing that particular observation in the second state, which is 0.2. We're going to do the same calculation again with respect to that. And we're going to do the same thing again with respect to that. This time S3, the second symbol in S3. All right, great. So then we end up with these new forward variables. Notice how this was the forward variables before. Now these are the forward variables now. Okay, so now we've got all of our forward variables for the 3 different states. So this was this is the time and this is the state. This is the time, this is the state. This is the time, this is the state. I think when you look at this the first time, it looks really intimidating. When you look at it the second time, it's not. And then the third time, it's like nothing. It's super easy. All right, so now let's do exactly the same thing again, 3 times. Calculate these forward variables 3 times. We're going to calculate this one first, then this one, and then this one. And what we're going to do is we're going to do it for the different states. We're going to start off with S1. So look at this. And with this time now, because we're dealing with a 2, this is the column for 2. And this is the column for S1. Right? So this entire slide is going to be about S1 on this column 2. So we plug in the variables for it. We end up with this number. We do it again. We do it again for the second time, for the second state. All right, second state, second symbol, and then finally third state, second symbol, and then we're done. Right. So you end up with these numbers, and what you simply do is you add them up. You get this number, and then you have the probability of seeing this sequence for this hidden Markov model delta, and that the probability of seeing it is 0.017658. You can do this with like a lot of different kinds of scenarios. I know here I just chose the symbols 0, 1, and 2, but you can do it for heads and tails and so on. Okay, the main thing I want you to do is really to understand the meaning of this, like being able to. So this is basically the same thing that we did in the Bayesian networks lecture when we calculated the probability of an assignment, except this time, because it was unrolling over time with the states, it was a bit more of keeping track of where everything is. But it was exactly the same thing, calculating an assignment, in this case a sequential assignment. In that case it was just a normal static assignment. Okay, great. So the same kind of thing can be done with continuous variables for Kalman filter, which I told you is used to track aeroplanes in the sky. It's a very powerful method. It's still used today. And the only difference is that the transition model is Gaussian. So the observation model and the transition model, they have Gaussian dependencies, and it looks exactly like the Kalman filter, except here the transitions are continuous. So yeah, so then there's really nothing to it. It follows the same kind of reasoning. It's just the representation is different. Okay, great. So let's move on to the last part of the problem, and this is now, we're almost done. I want to introduce this notion of plates. So remember when I spoke about this at the beginning, if I can go right back to the problem statement, I spoke about two different problems. The first problem was this notion of trajectories, right? We worried about being able to describe these trajectories and the switching between states and stuff like that. Okay, so that was what we covered. And then the second problem we had was representing redundancy in a problem by using templates. And so we can use a graphical model, this new notation that I'm going to teach you about called plate notation, to be able to have a graphical model that unfolds as we need it, even in non-sequential problems, non-dynamic problems, but for problems like, for example, modeling a family tree where there's lots of repetition. So that's where this notion of plate notation comes from. So let's quickly have a look at it. It's not a very long section. It's just a very quick section. So we will look at this for directed PGMs, but obviously you can extend this kind of framework for undirected models. And the main idea is that of using these little plates behind the variables. Okay, so let's look at these three different things, and let's talk about what we see. So let's look at this one first. So what does this mean? Well, this is the parameter for x. So this distribution, this parameter, whatever this parameter is, maybe if x is binary, then x0 occurs with 0.8% of the time, x1 occurs with 0.2% of the time. Okay, so maybe we end up with something like this: x0, 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 x1, and so on. Okay, so in this particular case, when we look at it like that, then the same distribution generates a single random variable. Okay, so this distribution generates this variable, and this variable can take on these different values. Okay, when we put a plate behind the distribution, that means that we can switch it up, and we can have the data that comes from this variable now comes from multiple distributions. So for example, this distribution had x0 is equal to 0.8, right? But this distribution has x0 with 0.5. But both of them are being used to define a random variable. So this means that when we can switch between these different distributions to generate different values of x. Sometimes 0.0 will occur 80% of the time, but then sometimes it will occur 50% of the time. So maybe an x1 will slip up more often for the x0 is equal to 0.5% of the time compared to the 0.8% of the time. So in this particular plate example, different kinds of distributions are generating the same random variable. And then finally, we have this scenario where we have the same distribution, so x0 occurs 0.8% of the time, but it's generating different types of data, different types of features. So here, for the x1 variable, you have XO occurring 80% of the time. For X2 variable, you have X0 occurring 0.8% of the time. And for X3 variable, X0 is occurring 0.8 of the time. So we're having kind of the same variable, but it'll never obviously be the same data, because just because of statistical noise, you might have some more X1s compared to the other ones. But I mean, if on average, if you keep sampling to infinity, you would expect it to converge. But anyways, that's really the idea. So you see the same kind of structure here gave us three different interpretations based on how we used plate notation. All right, so we can use the same kind of notion, this idea of plates, to template out different parts of the model. So here's an example of using plate notation to sample out three different models, and all of them are independent of each other. And here, what we're trying to do is we're trying to model the intelligence of the student with respect to the grade that they get for different students, right? So maybe for students, different kinds of students. You have Zolani here, you have Debocho and whatever. You have different kinds of models to model their intelligence with respect to their grades. And so you can use a template like this. Here's a more interesting example. So a course here has multiple students. So for example, like my course, and each of them have their own grade. Okay, that is true. All of you will have your own grades, and the grade depends on the difficulty of the course, right, which is common to all of the different types of students involved in the course. So if you try to enroll this one, you would end up with something like this, where the difficulty here is common between this grade and this grade, and the intelligence here is independent of the other intelligences and the other grades. Okay, but the problem with this, can you look at this? I've written it in red actually, the problem, so I can't even ask you what do you think is wrong with this graphical model. The problem is that the intelligence is not supposed to be associated with the course and a grade pair, right? I mean, isn't it weird that the intelligence here is associated with the difficulty of the course? I mean, like, it's not like you, inside of graphical models, because it's a more difficult course, you are more intelligent. And then when you go to any of the other honors courses, maybe high performance computing, because it's an easier course, then all of a sudden you're more intelligent, right? It doesn't work that way. Your intelligence is not really dependent on, it's not really dependent on the difficulty of the course. So intelligence is not supposed to be associated with the course and the grade pair, and so it's better to remove intelligence from the grade pair. And so you can do something like this, where intelligence is completely out of it. These intelligence and difficulty are no longer correlated, and we end up with them being separated from the grade. So your intelligence belongs to your student, and the difficulty belongs to the course. And so if you unroll this model, you end up with something like this. All right, so of course, like we said before, here we can include the parameters as outside of the model, and we'll see more of this later on when we speak about Bayesian learning. But right now, let me just tell you that a good graphical model structure takes out the parameters and explicitly indicates it inside of the model. And that's a very Bayesian thing to do, because you think about the structure independent from the parameters, so that you can do you're more versatile with changing your mind about how things are represented. So you can write down the parameters, for example, the difficulty of the course as a variable in the network, and write down the intelligence parameters as a variable in the network, which is also a common cause for the different kinds of intelligence variables. So this is basically how you would do it, and the same goes for grade, right? All right, this is basically how you would do it. It's a very interesting. I know it looks very complicated for nothing, but it is specific to a problem where you have this kind of object-oriented design. And in student universities with students inside of it, we have students who are very different from each other, and so it makes sense to do things like this. All right, so I'll end off by showing you some aspect of my PhD thesis where I used graphical models to do really cool stuff. And one of it was inventing this hierarchical framework that can be used to, it also involves a lot of templates and stuff like that, but it's a hierarchical way of looking at classification. and what I call it the dynamic, hierarchical dynamical Bayesian network. And it's really cool. You can use it for all sorts of stuff, like understanding how different composers actually influence each other through high level things about their compositions. That's one application. Another is more accessible maybe to you if you read a lot, is that if you read different books, you might find that certain authors can influence each other, and so you can use a model like this to identify that underlying influence between the different models. And what's nice about this is it's completely explainable. A deep neural network might be able to uncover those associations, but it has no way of explaining to you what are these associations, why are they closely linked to others, and exactly what is the underlying structure that governs these influence relationships. So this is a very clever way of doing that. And yeah, if you're interested in doing your PhD or your master's in graphical models, you know where to find me. All right, so thank you very much, and I'll see you at the next lecture.